part 2 on the Monday edition of physics class. Alright, we have been learning as an object falls, it goes faster and faster, and these are velocity vectors. That's why we don't want to be hit by something on the ground that has been falling for any amount of time, because the velocity increases and the impact will be more unpleasant. So as an object falls, it goes faster and faster. So we qualify that today with the word theoretically. So theoretically, as an object falls, it goes faster and faster. However, considering air resistance, which we have been ignoring, this is not totally true. So today, I can let you in on the whole truth. Air resistance. What are some molecules that are in the air? Does anyone know from your chemistry or hydrogen is in the air? All right, I don't know what a hydrogen atom looks like. I think they're kind of small. I'll just make it a little dot. Dimitri, what's another molecule in the air? Do you know? All right, oxygen. Is there anything else that you're aware of in the air?
Nitrogen.
Nitrogen. Okay.
You said hydrogen.
I said nitrogen.
Other traits.
Other trace gases. Carbon dioxide, lots of that. Alright. Argon is one. And there's probably other ones. But another one that is bigger than all these is water molecules. Like in the air, moisture, water molecules. I'll give that a little bigger blob, H2O. Alright, so that's to get the idea that when we drop objects, if it was dropped in a vacuum, they would fall faster and faster. And I've trained you to think that way. Today I'm going to tweak that, because considering the object is going through and bumping into all these molecules, a lot of traffic, and it causes a traffic jam. As the object goes down, it has to push away the air molecules. There is resistance from them. So as this paper falls, you can see the effect of air resistance. However, as the book falls, we see much less air resistance. And the reason being that the shape, so air resistance, let's make a note, air resistance depends on the mass, shape, density. See if I can think of another qualifier that would affect it. Surface area, like as I was trying to do previously, is I was trying to, where's the paper? When I drop a paper, if I could actually drop it this way, I would reduce the surface area between the actual, I would reduce the surface area between the object and the air if I could keep it at a straight edge. But did you see for a while it fell like the book, and then it kind of got off tilt, it got tilted, and then the air resistance affected it more. So these are the things that we're going to talk about today. And what happens is, here's my paper that I was trying to drop. What happens is, as the object falls, there really is air resistance. So we have to consider it. Suppose, is there a way that I can prove to you, beyond a shadow of a doubt, that this paper would fall like the book? Is there a way I can get rid of the air molecules and let it fall? I propose that there is. What? All right, let's do that. Everybody stand up. Can you get on your chair, or is it not safe?
Why?
We want to be high when we do this. Can you get on your
Can't we just like
chair.
stand and consider it?
You can do that if you don't want to get on your chair.
Yeah.
Yeah, you don't have to. Right?
No.
Take a paper, take the paper you're taking notes on, or some
Are you
other
kidding me? We're
paper.
dropping all of our books?
And we are going to drop it
I don't want to
with
drop
the
it.
paper on top.
Fine.
So, there you go. You got room? You got room, Drew? Come on out in the front. So, our conjecture is the paper will fall at the same height as the book. Ready? 3, 2, 1, release. Alright. Did yours stay on?
These physics books are so like that.
Alright, thank you. So this has shown you that air resistance this paper will fall the same as the book if the air resistance is removed. The book pushed all of the air molecules out of its way because of its mass and density and made way for the paper to follow right with it. So, in addition then, let's conclude this idea by looking at the idea that every object has its own air resistance. We kind of come upon this idea just through living our life. We know if we drop one of those peanuts that you get in the packing bag, when you have a package and you put those plastic peanut things in, that one doesn't have very much mass and its shape is sort of odd, so it's going to catch a lot more air molecules than if I drop this piece of chalk, which is more dense and has more mass. So we have this idea just in life, and it should make sense. But the full story then, when I drop an object, so here's what I've taught over here. This is basically untrue if we're considering air resistance. So over here I'm going to write the truth. So what happens, as the object starts to fall, it has no velocity, then it starts to accelerate because the earth is pulling it downward, so it'll have a little bit of velocity. Then it will gain velocity, but the faster it goes, guess what happens to the air molecules? It's hitting more of these because it's going faster. So there's more resistance the faster that it goes. So more resistance, because it's really hitting a lot of them, and eventually the force resisting the acceleration is so great from the air molecules that it will accelerate no more. So I kind of told you it would accelerate continually, but it will not if it is falling in the middle of air molecules, where it's hard for us to find a spot on Earth where that doesn't happen. So guess what? It stops accelerating. So this velocity vector repeats itself forever to the surface of the Earth. It does no longer increase in velocity. And that is called terminal velocity. Sound like a good movie title? Terminal velocity. So write that on your notes, pull a sketch of it, and that is the velocity where acceleration stops due to air resistance. Terminal velocity. I kind of make a little note about it in that before we said a dropped object, the acceleration was constant. So over here, the acceleration is constant. So it's always going faster and faster. So velocity goes up forever. But over here, when we have air molecules, the acceleration goes to 0. it no longer accelerates, and velocity is constant. So it's a different scenario on this side of the board in La La Land than it is in real life. All right, we'll talk a little more about terminal velocity tomorrow, just very short, and we'll go into our review. Okay? All right, so look over your this idea, mull over it, and I'll ask you to regurgitate it to me tomorrow. So come in being able to tell me what terminal velocity is and why it exists. Okay. Bye, Adam. We're done. All right, you guys can pack up. The bell is